Alright guys, so we are going to be going over the statics final review. We're going to be going over chapter 2, chapter 4, chapter 5, and chapter 7. We're going to be going over chapter 2, problem 102, chapter 4, 22 and 17, chapter 5.3, and chapter 7, number 42. So we're going to start right on off with chapter 2, problem 102. This problem is going to give us is a hot air balloon. They give us the force P of the balloon, which is 800 newtons going up. And we have our dimensions in the X, Y, and Z plane. They ask us to find the tension in each cable, tension AB, AC, and AD. Feel free to go ahead and pause the video so you can draw this diagram and then catch back up with me if you need to. Otherwise, we'll get started with the solution. I'll zoom out a little bit so we can see kind of what we're looking at. So solution, we're just going to start off at section AB. And we need to find the coordinate planes in the I, J, and K values. So for part B, for point B, we are at negative 4.2 meters in the I direction. On the J direction of point B, we are looking from A to B, so it's going down 5.6 meters. So negative 5.6 meters J. And in the Z direction, we have plus 0 meters in the K direction. Now I'm going to go ahead and do the lambda AB portion, which is going to be the sum of the squares. So negative 4.2 squared plus a negative 5.6 squared plus 0 squared. That comes out to 7 meters. So what we can do is take our coordinate plane that we just got from above and put that all over 7 meters. Okay. Go ahead and add me a page. Okay, so now we're going to do the same thing for AC. Oh, that's AD. How about AC? There we go. Alright, so for AC, we have a 2.4 meters in the I, minus 5.6 meters in the J, and a positive 4.2 meters in the K direction. I'm going to do lambda AC, which again is the sum of the squares. So we have a 2.4 squared plus a negative 5.6 squared plus 4.2 squared. Now when you're doing sum of squares, you don't really necessarily have to have the negatives inside. Since you're squaring it, it's going to come out as positive, but we're going ahead and doing that. I'm going to actually write to this side. This will come out to 7.4 meters. So just like we did for section AB, we could do the same thing for section AC. We're going to have 2.4 negative 5.6 and 4.2 all over 7.4 meters. And that's for section AC. And now we can do section AD, which we have 0 meters in the I, minus 5.6 meters in the J, and negative 3.3 meters in the K direction. Lambda AD is equal to the sum of the squares, 0 squared plus a negative 5.6 squared plus a negative 3.3 squared. All that comes out to 6.5 meters. Rinse and repeat. We will have that above a vector form all over 6.5 meters. That is section AD. Okay, so now we need to do sum of forces. I'm going to go ahead and zoom in a little So we have our sum of forces in the x direction, all equal to 0. It's going to go positive to the right. So we're going to take all of our I components from tension AB, AC, and AD and put them into sum of forces. So we're going to have a negative 4.2 over 7I, well, I'm actually going to keep the I off, times tension AB plus 2.4 over 7.4, I believe, yep, 7.4, tension AC plus 0, tension AD, all equal to 0. We're going to do sum of forces in the y are equal to 0. I'm going to go positive up. We have a negative 5.6 over 7 tension AB, that's AD, AB, minus 5.6 over 7.4 tension AC, minus 5.6 over 6.5 tension AD. Now we also have the 800 newtons at the top of the air balloon going up, all equal to 0. And now our sum of forces in the z direction, which I'm just going to say it's going to be down to the left, is positive. We have 0 TAB, or 0 over 7, same thing, plus 4.2 over 7.4 tension AC, minus 3.3 over 6.5 tension AD, so all equal to 0. So now we have our sum of forces. We have three equations with 3 unknowns. Now we have to do a system of equations. You can do solve these system equations using substitution, elimination, or a matrix. To make things fast and easy, we're going to use a matrix. So in the matrix, all you take is the coefficients of each of those, since we already have these set up, all of these coefficients, and just plug them directly in. So I'm going to go ahead and just copy and paste all of this in there for time's sake. But we don't need all this equal to the 800 newtons. Well, that's off. So that's our first matrix. We're going to take the inverse matrix of this portion. That's going to be our 0. This is a negative 800 newtons. All I did was move this 800 newtons to this side. 0 again. And this will equal our tension matrix, which is tension AB, tension AC, and tension AD. Putting that matrix into the calculator. If you don't know your matrix, feel free to look to the other video I have posted about solving a matrix using a TI-84. We get tension AB to be 200.9 newtons, tension AC to be 371.7 newtons, and tension AD to be 415.5 newtons. It's good practice to carry out your decimals out to the third decimal place, but as long as you stay consistent with your decimal places throughout the problem, you can do whatever amount of decimals you want. You can put it to whole numbers, you can put it to the first, second, doesn't matter. Just make sure you stay consistent. Other than that, that is problem 1 of the review. And now we will go on to the next problem, which is going to be 4.22. Okay. So number 4.22, they give us that it's a hinge at C, and we have a force P of 500 newtons at B. They ask us to find the tension AD and the reaction at C. So we make the free body diagram. If you need to know what the actual diagram looks like, just go to your book and find the problem number. I went ahead and just went and did the free body diagram to get us started. So we have our beam. We have our given dimensions. We need to find tension AD and reactions. So first thing I want to go ahead and do is solve for this alpha angle. Now I'm doing this alpha angle just for an added bonus in case you actually see it better from going up and to the left from D instead of down and to the right from A. The way that I'm going to end up doing it is from down to the right from A, but you can do it from D as well, it doesn't matter. So to find alpha, all we do is take our 90 degrees plus 30 degrees. They gave us the 30 degrees from the horizontal from the problem statement. That comes out to 120 degrees. Then you take 180 minus 120 degrees. That will come out to 60 degrees for alpha. Well, 60 degrees. Okay, I'm going to do it from A. So at A, knowing our law of interior angles, it's 30 degrees from the horizontal. If we shifted our beam at this angle 30 to be the new horizontal axis, so this would be the new x, this would be our new x instead, then this portion is also 30 degrees. I'm going to go ahead and keep it in standard xy coordinate planes, but our angle alpha, our angle from A, is still going to be at 30 degrees. So we go off of our solution. We have our sum of forces in the x direction, all equal to 0. We state positive to the right. We have positive Cx minus 500 newtons plus our tension AD, and this one's going to be at sine of 30 is equal to 0. It's sine of 30 because we're looking at the amount, the perpendicular distance, or the opposite of our angle that we're interested in. So it's going to be this portion right here, which is going to be equivalent to our x plane, so it's going to be the sine portion. We have too many unknowns, so we can't solve. We need to go ahead and go to the sum of forces in the y direction, all equal to 0. I'm going to state it positive vertically up. We have a positive Cy and minus tension AD. Now this one's cosine of 30 degrees. So all equal to 0. Again, we have two unknowns, can't solve, so we need to take a moment. So we're going to take a moment about point C, because that's going to take away the most unknowns. We're going to say it positive to the left. We have a negative 500 Newton force times the angle that it's been going at. So it's 30 degrees from the horizontal about point C. So it's going to be 500 newtons times the sine of 30 degrees times its perpendicular distance, which is going to be 200 millimeters, plus our tension AD, sine of 30, times our perpendicular distance of 250 millimeters, all equal to 0. Now we can solve for tension AD. Solving for tension AD, we get 400 newtons. Now that we know tension AD, we can solve for Cx and Cy. So plugging tension AD into our sum of forces in the x and y equations, we get Cx to be 300 newtons and Cy to be 346 newtons. Okay, so this one's pretty straightforward for a chapter 4. All it is doing is the sum of forces in the x and y, taking a moment, and knowing trig. He's going to give you a problem very similar to this, or the problem we're about to do, which is going to be the bell crank problem. So the biggest thing to watch out for is just your trig parts. You know, your sine, your cosine, finding your interior angles, everything like that. So as long as you have a good grasp on finding your trig portion, you'll be just fine. So continuing on, we're going to go to problem 4.17. 4.17 is very similar to 4.22. However, this one's a bell crank, and we're giving a little bit of a different dimension. So they gave us a tension AB at 150 pounds. We have a pin at C and an unknown tension at D going to E. They ask us to find tension DE and our reaction at C. So with our phi bi diagram already stated, we'll go ahead and start off with the solution. Zoom out a little bit so we can see it. So let's just start off with the sum of forces in the x and y. So sum of forces in the x, all equal to 0, positive to the right. We have Cx minus 150 pounds times the angle that it's going at. So if you look at this triangle carefully, it's at 90 degrees, and we have a dimension of 4 inches. So that means that our triangle is going to be a 3, 4, 5 triangle. 4 and 5 triangle. The only reason why I'm doing that is because they have 90 degrees and one of our dimensions is 4 inches. So the easiest way to see it is a 3, 4, 5 triangle. Otherwise, you end up having either it's a 45, 45 or a 30, 60, 90 triangle. And when you do sine or cosine of any of those combinations, you're going to get a little bit of a different number. So this way is just a little bit easier, but by all means you can do it. Whichever way you see is easiest is the way that you should do it. I'm going to do it the 3, 4, 5 method just because it's a little bit easier for me. You can do what you want. So solving that out, we can actually solve for Cx. We get that to be 90 pounds even. So there's one of our answers. Now we take our sum of forces in the y direction, all equal to 0, positive vertically up. We have Cy minus tension dE, this is going vertically down, and our minus 150 pounds at an angle of 4 over 5 equal to 0. We have two unknowns we can't solve, so we need to take a moment. So we have a moment about C. It's going to take away two unknowns, which we want to do, equal to 0, positive counterclockwise. We have 150 pounds times its perpendicular distance, which is going to be the 5 inches. This portion right here is perpendicular distance. Minus our tension dE times its perpendicular distance, which is going to be our 6 inches, all equal to 0. We can solve for tension dE. We get tension dE to be 125 pounds. And now we know tension dE, we can solve for tension, or not tension, sorry, reaction Cy. Solving for Cy, we get 245 pounds. So same thing as before, it's pretty straightforward. It's just sum of forces x and y, and taking a moment. All you gotta worry about is your trig. So really make sure you have your trigonometry and your laws of sines and cosines down, and you will be good to go. Okay, moving right on along, we're gonna go to problem number 5.3. Now Jackson did in his review problem 5.3 this semester, but he took his origin at a different spot than I'm going to be doing. I'm going to be taking the origin about the bottom left-hand corner. Sorry about that, I need to take a drink. So I'm going to be taking my origin about the bottom left-hand corner. Okay, so when we look at problems, they ask us to find the centroid and the moment of inertia total about the horizontal axis. So we need to break these into shapes that we can recognize. Well, the easiest shapes to see that we can break it up into are going to be a rectangle and a right triangle. I'm going to say our rectangle is shape 1 and our triangle is shape 2. I'm going to go ahead and try to guess where our local centroids are going to be. So our local centroid for the rectangle is probably going to be right about there, about the center there. And then the triangle is going to be up and to the left a little bit, more where the center mass is, so probably right there. So we're going to say local 1, local 2. This is not something that you necessarily have to do. This is just going to kind of confirm my assumptions for this problem. So let's state what we know. So we know we have the rectangle and the triangle, and nothing is going to be taken away. So all this is going to be adding into the system. Now I will say that for the final, there is a high likelihood chance that he will have a centroidal problem dealing with moments of inertia, And within the centroid, or within just the main shape itself, you're going to have a hole in it. So that means that, say your rectangle and this bottom right hand triangle are going to be solid shapes, but then you might have, say, this circle in the center, and it's cut away. So like this, all this is blank. So that means you have a hole. That's going to change your centroids and your moments of inertia pretty effective. So watch out for that. Basically, the only thing is when you do your tables like what we're about to do, just the whole portion is just going to be subtracted. So I like to go ahead and get our areas out of the way, just to make things a little bit easier on us. So I'm just going to label it A1 is equal to our 120 times 100, which is going to be our 12,000 square millimeters. And our area 2 is going to be base times height over 2. Our base is 60 millimeters. Our height is 120 millimeters. All of that over 2. We get area 2 to be 3,600 square millimeters. I'm trying to mute my phone here so we don't get interrupted. Okay, so now that we have our areas of each shape, what we're going to do is going to go ahead and make the table to keep ourselves kind of organized. Now, you don't necessarily have to do each portion, X bar and the Y bar area. We have X bar times our area and our Y bar times our area. If you have a shape that is symmetric about some portion X or Y, you can state it that it's symmetric about whatever that point, and then that is a point where you don't have to worry about in your table process, because say if you're doing it from the horizontal, if it's symmetric about the X, you don't have to worry about it. You only have to worry about your Y, and you're good to go. But most likely for the problem he's going to give you in the exam, he's going to want you to find both of them, just so you can show that you know what you're doing. So we're going to do it both in this problem. So each portion we're going to find our locals. So our local X bar of the rectangle is going to be, trying to fit this all in there, 16 millimeters. Our local Y bar is going to be, so now we're starting from 0. It's from the very bottom left-hand corner right here. So in the X direction, the Y direction, we have to go up 60 to get to the bottom of it. Now we got to go up half of 100, so 50. So we're going to do 50 plus 60 to get 110 millimeters. We know our area, 12,000 square millimeters. I'm going to go ahead and do the triangle part, and then I'll do the sum of X bar areas and Y bar areas. So our X bar of the triangle, we're going to have to refer to our table in the book, which in this portion, it's going to be our height over 2, sorry, not over 2, over 3. So we're going to have our 120, wow, that looked terrible, 120 over 3, which we get this to be 40 millimeters. So 40 millimeters. And our Y bar of our triangle is going to be 2/3 times the base. So 2 times 60 over 3, which just so happens to also be 40 millimeters. Okay. We know our area, 3,600 square millimeters. And I'm going to go ahead and zoom back in now. So now we just do our X bar times our area. So we get 7.2 times 10. Oh, let's see here, 5 to the 5th. This is going to be cubed millimeters. And for our X bar of triangle, it's 1.44 times 10 to the, let's see here, what is that? 345 as well. Cubic millimeters.
Now our y bar is 1.32 times 10 to, I believe that's the 7th, 4, 5, 6 cubic meters. And 1.44 times 10 to the 5th, I believe again, 345 millimeters cubed. Okay, so we'll go ahead and take our sum of our area. Oops. Sum of the area, which we get 1.56 times 10 to the 3 to the 4th square millimeters. Let's take our, god dang it, I can't write, sum of our x bar times our areas, which we get 8.64 times 10, or what is that, 4 to the 5th, I believe, cubic meters. And our sum of our y bar times our area, which is going to be 1.46 times 10 to the, let's see here, 4, 5, 6 cubic meters. Okay, now let's find our globals. So our global x bar is equal to our sums of our x bar times our area over sum of the area, which comes out to 55.4 millimeters. And our y bar is going to be the same thing, using a y bar times area over sum of area. We get 93.8 millimeters. That y bar, global y bar, is going to come in handy for us in a second. So we're going to go back up to our main problem, and we're going to redraw it for our moments of inertia. So we're going to have the exact same thing. I'm going to make this more central. How about that? Add page. Okay. So I'm going to take away my guess. So our global is at 55.4 in the x and 93.8 in the y. So if our 60 is right here at the center, we're going to go just to the left of that. So just over here. And then 93, what you're going to do is you're going to take your y bar in the x, so 110, and that will be kind of a good judge, plus the 60 to get 93. So that's going to be somewhere, let's see here. It's going to be, so it looks like our global is going to be about right there. So let's see where I kind of exactly have it. Yeah, just to the left. So this is going to be our main C. Now our local C's are roughly there. We have C1, and right here, C2. So we're going to draw our axes through our locals. This just kind of helps us see it. Drag that down a little. We have our global y bar. Okay. Now we need to find our moments of inertia. I'm going to go ahead and make this a little bit smaller. Maybe not. Okay. So to find I sub global total, we need I sub C1 plus I sub C2. So IC1 is IC1, which I'm just going to put it as 1, plus our parallel axis theorem, area 1 times d1 squared. So if you look at the book for moments of inertia of a rectangle, you can do it about x or x prime. I went ahead and just did basic x. So that is going to be base times height cubed over 36 plus our area 1 times our distance 1 from the local to global squared. So that is 120 times 100 cubed over 36
plus 12,000 times our 110 minus 93.8 squared. The 110 minus 93.8 is our local centroid in the y direction of our rectangle minus our global centroid. That will get us our distance between global and local in the rectangle, this portion right here. Solving that out, we get IC1 to be 1.31 times 10 to the 7th millimeters to the 4th. And now we can find IC2, which is going to be I2 plus parallel axis theorem, A2 times D2 squared. If you look at the triangle portion for the centroid, sorry, not centroid, the moments of inertia of a triangle, it is going to be for the y-axis or your x prime or just x, it's going to be base cubes times height over 36. I did 36 somewhere. I shouldn't have. I did. I was ahead of myself. This portion up here on IC1 is not over 36, it's over 3. I apologize for that. I was ahead of myself. This part is over 36 plus our A2 times D2 squared. Okay, so our base of the triangle is 60 cubed times our 120 all over 36 plus 3600 times our distance from our local centroid to our global centroid. So that is going to be our 93.8 millimeters minus our 40 millimeters squared. We get IC2 to be 1.11 times 10 to the 7th millimeters to the 4th. Adding those up, we'll get our total. We get IC total to come out to 2.43 times 10 to the 7th millimeters to the 4th. Okay, so the biggest problem to see for this kind of problem, like I said, watch out for a hole in the main geometry, and just know where to look on the table to know which moments of inertia equations to use. Other than that, as long as you get the centroid and you have the base of the moments of inertia, even if you don't get the numbers right, you'll get most credit. So don't stress out too hard, and you'll be just fine. So continuing on, we have our last problem, chapter 7, number 42. We are given this beam with a distributed load on the right of 150 pounds per foot, our point load at C at 450 pounds, given our supports at A and D, which is a pin and a roller. They ask us to find the shear and bending moment diagrams and our shear and moment max. So in statics, you can draw the beam as just a single line. Draw your reactions, so we have CX, sorry, not CX and CY. I don't know why I wrote that. Probably from one of the other problems. But that's AY, AX. Okay. And we have a roller at D, so it's just a perpendicular reaction. And a pin at A, so it's AX, AY. And we have our point load and distributed load. Now our distributed load can also be represented as a point load, so as a force resultant, which can be found by doing 150 pounds per foot times its distance it's covering, so 4 feet. It just occurred to me that I did not put the dimensions like I've been doing because I'm lazy, I guess, I don't know, but this is 4 feet, 8 feet, and 4 feet. I apologize for that. You're probably like, wow, why is it so confusing? It doesn't have dimensions. So now solving that, we get 600 pounds as a force resultant. Now we can do a much easier sum of forces in the x and y and take a moment. So we have our sum of forces in the x direction, all equal to 0. A of x is the only thing acting in the x direction, so it's 0. Sum of forces in the y, all equal to 0 because it's statics. 0. We get positive AY minus 450 pounds plus dy minus our force resultant, all equal to 0. Too many unknowns. We need to take a moment to solve. We have a positive counterclockwise. I'm going to take this about A, all equal to 0. We get negative 450 pounds times a perpendicular distance of 4 feet plus dy times its perpendicular distance of 12 feet minus our 600 pounds, which is our first force resultant, times its perpendicular distance of 14 feet, all equal to 0. Now we can solve for dy. We get dy to be 850 pounds. And now we can solve for ay. We get ay to be 200 pounds. So now we have two options after this. So now we need to find our shear and bending moment diagrams. We can do our internal cuts for before point C, after point C, and before the distributed load. Or we can just look at the values given from our free body diagram and our reaction calculations to just write out the shear and bending moment diagrams as we can see from those solutions. So we'll just write out like normal. So for your shear, the units are in pounds. This is going at some distance x, which is in feet. Okay, so at AY, which is the very first point at A, we have 200 pounds. So it's going to start off right at 200 pounds. Now to point C, it's going to be constant, 200 pounds. Now at point C, we have our point load of 450 pounds. So you take 200 pounds minus 450, we will get a negative 250 pounds all the way to point D. So negative 250 pounds. Oof, like that. Now, at point D, we have our support roller, which is going to be 850 pounds. So take 850 minus 250, we get 600 pounds. And this is not drawn to scale. We have 600 pounds. And we have our distributed load, which is 600 pounds going down. So all that goes to 0. Now we have our shear. Now we need to do our moment. If I could scroll down enough. Moment equation, moment diagram. Our moment is in pound foot, not per foot, but pound times foot. We have our x distance again, which is in feet. So the easiest way to find the moment diagram is just take the area under the curve. So we have 200 pounds times the distance that it's traveling, which is 4 feet. So we have our AY, which is 200 pounds, times our distance, 4 feet. Multiply those together, we get 800 pound-foot. And that's going all the way to point C. So at point C, we go up to 800 pounds. Pound-foot. Now take our area under the curve for the 250. It's traveling at 8 feet from our diagram. So negative 250 times 8, we get a negative 2,000 pound-foot. So take 2,000 pounds negative 2,000 pounds plus 800. We get 1,200. Going this way. So negative 1,200 pound-foot. And we look at our shear again. We take a base times height over 2. So our base was 4 feet times our height, which is 600 pounds, all over 2, we get 1,200 pound-foot. If I can write it a little better, 1,200 pound-foot. So now we go from negative back to positive 1,200. Oops, I'm sorry, that's not. So my snap settings on my iPad did that. But so if you look at our shear diagram, that is a linear line, so it's not a constant. So when you take a derivative of a constant, you get a linear, and if you take a derivative of a linear, you get squared. It's actually not a derivative; it's more like an integral. So the linear now becomes a quadratic, so it's going to be curved a little bit like that. Okay, so now we know our shear and bending moment diagrams. We need to find our shear and bending moment max. So the easiest way to find that, you can do your internal cuts and do it mathematically, or you can just look at your diagrams and see what we have as our max peaks. So for our shear max, we need to find what our highest peak is on the diagram, which is this 600 pounds. So that is our shear max. This shear max is 600 pounds. And our moment max is where our moment is max. And now you just look at the magnitude. You're not really guessing about positive or negative, it's just the magnitude. So it's going to be 1,200 newtons. Sorry, not 1,200, 200 pound foot. So 1,200 pound foot. Okay, and that's it. So that way is they're doing the shorthand method of shear and bending moment diagrams. You can do it the long way and do internal cuts and use your equations to get it, but if you do it the shorthand way, you'll still remain and get full credit. That concludes the final review for statics. I wish y'all good luck. If you have any questions, feel free to shoot me a message. At any point in time this video gets a little confusing for you, pause it, try to catch up. And that is it. Good luck, guys, and I will see y'all in the next time. Thanks.